Hello again. In this video, we are going to discuss the Berthelot equation of state for a gas and derive its critical constants. The equation bears a very strong resemblance to the van der Waals equation, where we again have two parameters, A and B, and the equation involves the gas constant R, the thermodynamic temperature T, the molar volume V. Notice here we're just putting V instead of V sub m for simplicity, to make it easier to read, but this V is actually the molar volume, and the pressure P. I have slightly rewritten the equation in this more suggestive form to make it easier when we begin to take derivatives. To that end, to find the critical points, we are going to take the partial derivatives of the pressure with respect to the volume and set them equal to 0. First for the first derivative and for the second derivative. So we take the first derivative of this expression with respect to the volume. And we notice that we have a function of v, which we'll call u here. So the derivative of u to the minus 1 is minus u to the minus 2, and then we take du dv. But since we just have a linear v here, that's just equal to 1. So for this first expression, we get minus rt, v minus b to the minus second power. Then here we have v to the minus second exponent. So the derivative is going to be minus 2 v to the minus 3. We have the minus 1 in front. So that gives us plus 2 a over t times v to the minus 3. And this gives us a version of the first derivative that we're going to use to now take the second derivative, using the fact that the second derivative is the first derivative of the first derivative. Again, using the properties of the derivative of powers of a function, we have our minus 2 times a minus 1 gives us a plus 2 in front. The minus 2 now becomes a minus 3, so we have plus 2rt, the quantity v minus b to the minus third power. Then for this particular term, our minus 3 multiplies our plus 2, so we get a minus 6a over t, and the minus 3 becomes a minus 4. At the critical point, both the first and the second derivatives of the pressure with respect to the volume will be equal to 0. And now we will solve this system of equations, first to find the molar volume at the critical point, which will be the critical volume. As a matter of technique, it is actually easier, instead of solving directly for v, or setting each of these two equations equal to each other because they're both equal to 0, it's actually easier to solve each of the equations first for rt squared, which may seem like a strange way to do it, but it makes the algebra much, much less complicated. So that's what we're going to do. We're going to solve each of these expressions in terms of rt squared, and then since each will be equal to rt squared, we'll set those expressions equal to each other and then solve for the critical volume. So now we can add a positive rt, the quantity v minus b to the minus 2 power to each side, and instead of writing things as negative exponents, now we'll simply write them as fractions, because that is easier when we are doing algebraic manipulations. To get 2 times a over t v cubed equals rt over the quantity v minus b quantity squared. Then, multiplying each side by the quantity v minus b squared, we get that rt equals 2 times a times the quantity v minus b squared over tv cubed. Multiplying each side by the temperature T gives us that RT squared equals 2A times the quantity V minus B squared over v cubed. Let's keep this equation in mind because we're going to use it in a little bit, and we shall refer to this equation as equation 1. And we recall the expression that we had derived for the second derivative of the pressure with respect to the volume, 2RT, the quantity V minus B to the minus 3 power, minus 6A over T times V to the minus 4 power. At the critical point, just like the first derivative, the second derivative is going to be equal to 0. Again, we are going to manipulate this expression for one involving RT squared. Here we've combined two steps. First, we've added 6a v to the minus 4t to each side, and then we've multiplied each side by the quantity v minus b to the third power. So now we get 2rt equals 6a, the quantity v minus b cubed, over t v to the fourth, where we've replaced the v to the minus fourth by a v to the fourth in the denominator, just to make the algebra less complicated. We divide through each side by a factor of 2, so that removes our 2, turns our 6 into a 3, and multiply each side by the temperature T. That gives us that RT squared is equal to 3a times the quantity V minus B cubed over V to the fourth power. And in keeping with what we've done before, let's refer to this equation as equation number 2. Recall, in equation 1, we had an expression for RT squared. At this point, we are going to set those two values, those two equations, 1 and 2, equal to each other. Where here we've set RT squared equal to this expression, recalling that we had this expression from equation number 1. So I'll just put that in a circle to remind us where that expression came from, and this expression came from equation number 2. While this equation looks very, very messy, we can make a number of simplifications. We can cancel through the a's, and they disappear. We notice that we have v to the fourth and v to the third, so we can eliminate v to the third and reduce that just to the first power. Also, we have v minus b cubed, v minus b squared, so we can eliminate to the second power and reduce that to just the power 1, which makes it much simpler as 3 times the quantity v minus b divided by v is equal to 2. Multiplying each side of our relationship here by v gives us that 3 times the quantity v minus b is equal to 2v. We use the distributive law to make the left-hand side 3v minus 3b. And we get that v is equal to 3b. Since this is at the critical point, this particular volume is the critical volume. So the critical constant for the Berthelot equation for volume is equal to 3b. Now we want to solve for the critical temperature. And we can use either our expression for the first derivative or our expression for the second derivative. Because it's a less complicated expression, we're going to use the expression for the first derivative. So recall, we have minus RT over the quantity V minus B squared plus 2A divided by T times the volume cubed, and it is equal to 0 at the critical point. Now we substitute the value that we had found for the critical volume of 3B, and now we're going to substitute it into the first derivative equation. Since V is equal to 3B, V minus B up here is equal to a quantity 2B, which is squared to give us 4B squared. And then for the V cubed here, we cube 3B to give us 27B cubed. Then we add RT 4B squared to each side. So now we get RT divided by 4B squared equals 2A divided by 27B cubed times T. Now we multiply each side by 4B squared T, So now we get RT squared on the left-hand side. And the right-hand side is equal to 8AB squared divided by 27B cubed. And we notice in the next step, we are going to divide through the numerator and the denominator by a b squared to leave us just with a b in the denominator. This gives us that RT squared is equal to 8a divided by 27b. Our next step is to divide through each side by r and then take the square root of each side. And we find that the temperature at the critical point is equal to the square root of 8 divided by 27br. And since this is at the critical point, this is the critical temperature. There are other ways to simplify this expression, but for later use we're going to keep it in this particular form. Now we recall the Berthelot equations of state. And notice that this relationship is true for any combination of temperature and volume. So let's suppose that we do this at the critical temperature and at the critical volume. The particular value that we find for the pressure would then be the critical pressure. Now note that we could have also used the expressions for the first derivative or the second derivative, but that it's just going to be easier algebraically if we just use the Berthelot equation itself to solve for the critical pressure. Note that the amount of algebra involved in this step is not extremely extensive, but in some of the resources that I checked, they did solve for the critical volume and the critical temperature, but for the critical pressure, they simply wrote down this expression and left it at that. But we will go through in detail and actually solve for the critical pressure for the Berthelot gas. Now we substitute the values for the critical volume, which is 3B, which gives us 2B here, and in the place of the volume squared, we end up getting 9B squared. Then we substitute the value for the critical temperature, which is this very messy square root of 8a expression. So we have it here in the numerator, and then over here in the denominator. Note that when writing it down here, we've switched the places of the v squared and the t just to make this clearer to read. Now we multiply each side of our equation by this square root of 8a over 27br. And the advantage of this is it now removes this particular expression from the denominator. And as well, it converts this particular square root, since we multiply the square root times the square root, we've removed the radical sign. So now we've removed the radical from this particular expression in the denominator. And the square root here has now become 8a over 27br, not the square root. So we have a square root at the left, but we've removed the square roots from the right-hand side. And we shall see that we can simplify the expression on the right-hand side a little bit more. Notice that the r's here cancel. Be careful because the b's don't cancel because they're both in the denominator, so we get a b squared. The 2 cancels the 8, so we get 4 divided by 27, the b squared, and then the minus a over 9b squared. And by finding a common denominator for these two fractions, we will be able to simplify the right-hand side even further. The least common multiple of 27b squared and 9b squared is going to be 27b squared. So we multiply this fraction by 3 divided by 3. So now we have 27b squared as the common denominator. And we can simplify the right-hand side, which was previously very, very bad, as a divided by 27b squared. So hold on, we're almost there. We're very close to solving for the critical pressure. Summarizing where we are, we have that the critical pressure times the square root of 8a over 27br is equal to a divided by 27b squared. Now we want to get the critical pressure alone on the left-hand side of the equation, We want to solve for that particular quantity. So we're going to multiply each side by the reciprocal of the square root of 8a over 27br. So now we have that the critical pressure is A divided by 27b squared times the square root of 27br divided by 8a, which still looks very complicated. But now we're going to make some simplifications under the radical sign to hopefully make this look less messy. Now we effectively perform a prime factorization of 27 as 3 squared times 3 and 8 as 2 squared times 2 underneath the radical sign. And we'll be able to use the properties of the radical that we'll be able to pull the 3 and the 2 out as coefficients and remove them from underneath the radical. We can pull the factor of 3 over 2 out from underneath the radical sign. So that gives us a over 27b squared times 3 halves times the radical. And now we're going to use the fact that we can cancel the 27 and the 3 to give us a 9 in the denominator, which is going to multiply by 2, which gives us a divided by 18b squared times the square root of 3br divided by 2a. Once we've simplified as much as we can underneath the radical, one trick that we might employ is to try to, instead of pulling things out of the radical, try to push as much from in front of the radical underneath the radical sign. So we're going to use the fact that the x is equal to the square root of x squared. So we square this expression, but put it underneath a square root sign. So we notice the square root of a squared divided by 324b to the, and that's to the 4th power. We have to be very careful about that. Is exactly the same as the coefficient that we had before. It just looks different. And we're going to use the fact that the square root of x times the square root of y is equal to the square root of xy, so long as they're real numbers and they're positive. Bringing together all the factors under each of the individual square root signs under a single square root sign gives us that this is equal to the square root of 3 times a squared times b times r divided by 648 times b to the 4th power times a. And we notice that as complicated as this expression is, we will soon be able to perform simplifications upon it. Now we can use the fact that a squared divided by a is simply a. B divided by b cubed is going to be b to the 3rd power in the denominator. And that if we divide 3 and 648 by 3 each, we get 1 divided by 216. So here we have one version of the expression for the critical pressure for the Berthelot gas. And this is one of the expressions that I found in references. Now what is tricky is that other references give a different value, which was not immediately apparent that the value given in the other sources was essentially exactly the same value. It looked different. So let me now show you a couple more manipulations that we can perform to get this result to look exactly the same as the result I found in the other source, in case you come across that particular value yourself. The first step is simply to multiply the numerator and the denominator each by a factor of 2. So essentially we just put 2 here and multiply this by 2 to get the square root of 2ar divided by 432 times b cubed. It's not immediately apparent why that is so helpful, but we shall see in a second. We notice that 432 can be factored as 144 times 3. And the key insight here is to recognize that 144 is the perfect square of 12. Here we write out explicitly that 144 is equal to 12 squared, so we realize that we can pull this in front of the radical sign as 1 over 12. And this gives the final version of the critical pressure. This is the result from another one of the sources. It looks a little different than this, but has exactly the same value. 1 over 12 times the square root of 2AR divided by 3B cubed. I thank you very much for your kind attention through this very long video. As always, have a good one.